Last time we learned section 3.1, measures of center. Today we learn measures of spread. Let's look at an explanatory example. Two cities, San Francisco and St. Louis, average monthly temperatures measured throughout a year. Is their weather similar? Use statistical measures or graphs to make your case. Well, you can look at the data, come up with your own opinion. I say, look, we just learned about measures of center. Why not use them? So if we go to Minitab and get rid of that, I've entered their data in. So why not use both measures of center, right? I always say it's good to know both, right? So if we go to statistics and click mean and median, what do you know? Both their means and medians are almost identical. Their medians are literally identical, right? So let's just get that picture in there. And I think it's safe to say that using mean and median, SF and STL appear to have nearly identical weather, right? But note that San Francisco and St. Louis have different temperature ranges, right? San Francisco is 51 to 63, relatively small range, versus 30 degrees to 79 degrees. Right. So maybe there's a little bit more going on here. And the question is there a single number that we could use to denote the spread? Well, of course, you could just subtract the max minus the min. But maybe there's another slightly more advanced number that we can use that can tell us a lot more about the distribution. One of the main statistics that we're going to use in this class is the standard deviation. One of the most important measures in all of statistics is the standard deviation. Now, that does not mean that you need to memorize this formula, which you'll see is a little bit complicated, but you should understand it. And you should definitely understand the meaning of the standard deviation. I am going to write out the formula because it's important. And first what I'm going to do is I'm going to write out the formula for the variance. Now, this is a little unusual, but it turns out that the variance actually has two slightly different formulas depending on whether you're calculating the population variance or a sample variance. Population variance is denoted sigma squared, and I guess this is the point where I should say that the data set is x1 through xn, right? Suppose that you have these n data points. I'm using capital N to denote a population. Right, so anyway, it's going to be x1 minus your mean, right, your population mean squared. We're just going to do that for every single thing. Note that what we're doing is we're finding the difference between each data point and the mean. And then we're squaring it. And then we divide by the total number of data points. So, you might also see it written in the book like this. But you don't need to worry about that. Just to let you know, if you look in the book, you'll see that. Okay, now the sample variance which is denoted s squared. Very similar formula, but again, as I said, it is a bit different. I'm going to use a lowercase n to denote that we're using a sample. Right? We're not selecting every single thing in the data set, right? But anyway, instead of dividing by n, we divide by n minus 1. Right, and again, if you look at this in the book, you don't need to know this, but just to let you know, if you see it, that might be how you might see it written. Yeah, so we'll discuss why those two things are different in a sec. But just to be clear, the population standard deviation is denoted sigma, and of course it's the square root of sigma squared. You might have guessed that when you saw that it was denoted sigma. And then of course the sample standard deviation is S. And of course, that's the square root of S squared. So you do this crazy summation, divide by n or n minus 1, and then you take the square root of it, right? Lovely formula we've got going, right? Now anyway, why are these formulas different? Well, unlike the mean, the population and sample variances and standard deviations, I should add, have slightly different formulas. The reason is technical. A real stats expert could probably get into it, but the basic gist is that sample data tends to be a little bit less varied than population data, which makes sense, right? The population can have some really extreme outliers that typically won't get captured by samples. So one way to account for this is to divide by n minus 1 instead of n, i.e., and I think the book uses this term, use one less degree of freedom. Don't worry about what that term means right now. But again, if you're really interested in statistics and exactly what all this stuff means, talk to your local stats expert, which I'm sorry to say is not I at this point. Anyway, let's find the standard deviation of our data, right? So what we're going to do is we're going to go back into Minitab, Stat, Basic Stats, Display Descriptive Statistics. Still make sure those two columns are selected, but let's instead select standard deviation. Now, I believe that this calculation is the population standard deviation. But you can see that San Francisco and St. Louis have drastically different standard deviations. Right? San Francisco's is small, its spread is small. St. Louis's is large, its spread is large. That's what you would expect. Right? So if we go back into Minitab and maybe we get these values out there, we can see that using standard deviation, we see San Francisco and St. Louis have drastically different weather, I'll say thanks to temperature variation. All right, so just something to keep in mind there. Now, one thing I just want to point out, you might be wondering, wait, why did we square the difference from the mean? Why did we square the distance from the mean? You can say, well, because the distance doesn't matter. You don't care about whether it's plus distance or minus distance, right? But you could just take the absolute values. Why do we square them? Well, the reason is, if you remember the terms resistant and sensitive, remember how the median was resistant, the mean is sensitive? We want the standard deviation to be extra sensitive to values far from the mean in either direction. Right? So by squaring that difference, you increase the sensitivity. Okay. So standard deviation, again, extremely important. I've even heard statisticians say the mean doesn't make a whole lot of sense without the context of the standard deviation. So a lot of times when we talk about the mean from now on, we're going to be talking about the standard deviation as well. One of the beautiful things about it that we're going to see in a little bit is it provides us an idea of how close most of the data is to the mean. So now we're just going to take a little bit of a detour. Remember the way that we approximated the mean? I said we found. Really, we approximated the mean of grouped data. Remember we did this last video or 2 videos ago, right? I think it was last video, right? Well, for the standard deviation, we want to be able to approximate the standard deviation of group data. And it's basically the same thing. Or I should say the same process, you know. A couple extra steps here. Number 1, find the mean, which is either going to be sample mean or population mean. Still going to find the midpoint of each group. Instead of multiplying each midpoint by its corresponding frequency, we're going to multiply each midpoint minus the, I'll just say mean, squared. All right, whether that mean is population or standard. Right, just to be clear, it could be either. Add the products, that's the same. Divide by, and instead of the total frequency, we're going to be dividing by, I guess I should say, n minus 1 or n, depending on whether we're talking about a population. All right, and then last but not least, we do want to take the square roots. Okay, because we want to find the standard deviation, not the variance. This is finding the variance. And then this right here is the standard deviation. All right. So let's do a quick example. Go into Minitab. Right. We've got the weather data. I went ahead and grouped it by tens, right? 30s, 40s, 50s, 60s, 70s. Then I already went ahead and found the midpoints. Okay. And let me call this guy right here, I'll call it SF group. Oh, I think I double spaced that. Then I'm going to do the same STL group. Okay, let's just do that right there, okay? So here's a little trick for how you do this. So we're going to use the formula, go to calculator. We want to store this result. We're going to do San Francisco first. So let's store it in SF group. And now you can see I've tried this, right? We're going to do, let me actually delete all this so I can start from scratch, show you exactly what we're doing here. Parentheses, we're going to choose the, we're going to choose the midpoint minus, and then we're going to choose the mean, which we know for San Francisco was 57.5. And then we're going to square that. And then we're going to multiply by the frequency, which is San Francisco. Right, just that was that right there. You see that that's the 00750 right there? Right? That's what we've got. And see, that's what we're getting right there, okay? Then what we're going to do is we're going to sum all that data and divide it by either n or n minus 1. Let's just say n, right? Suppose it's, we're just going to say 12. Suppose it's population, right? So just want to show you those are the values. So now what we're going to do is we're going to say, okay, we want to sum all of this data and then divide it by 12. Let's see what, and we want to store this in, let's store it in maybe another place. Store it there. Okay. We get 27.0833. That seems a little bit high, right? Because that's the variance. So actually, let's go ahead. And now we're going to take the square root of all that. Let's see what that gives us. About 5.2. Okay. So maybe just kind of, okay, we got that. Just do that a little bit. Save the photos. And we're just going to stick this into our notes. Let me just stick that in there. So that's what we get for San Francisco. That's the approximate standard deviation for San Francisco. Okay? So, I'm going to be bold and say, try it for St. Louis. And we're going to move on. We're soon going to learn about the most important distribution, the normal distribution. Shape of a normal distribution is a bell curve. It is unimodal. Right? Most data accumulates near the mode, which is the highest frequency, and have, I guess I'd say, sparse data, right? Very, very little data. And the shape is unimodal. Now, if our data is approximately normally distributed, because nothing is ever perfectly normal, but if our data is approximately normally distributed, then we know the following. And I'm just going to go to Desmos for this guy. About 68% of the data is in that blue region. About 95% of the data is within that red region. It was in the red region or the blue region. And about 99.7% of the data is within the green, red, or blue region. So we take a photo of that, crop it a little bit. And we're going to save this guy. And stick that right in here. And there we go. So this guy right here is roughly 68%. These two guys wind up having 13.5% of the data in them when you do the math out. And then these guys, let's see. I think it winds up being 2.35%, right? 99.7, yeah. This is going to be 2.35%. 2.35% of the data is in there, right? So just to be clear, this is about 68% of the data. Maybe I'll use brown. This is roughly 95% of the data. And then, let's say this is roughly 99.7% of the data. Now, this is a nice picture and absolutely something you should measure, but what do these blue, red, and green pictures represent? What they represent is the amount of data within 1, 2, and 3 standard deviations of the mean. That's what's so important about all of this. So, in fact, let me move this, all of this over. So roughly 68%, maybe I should use blue for this. Roughly 68% of the data is within 1 standard deviation of the mean. So in other words, 68% of the data is between Let's say mu minus sigma to mu plus sigma. Okay. Similarly, and I'll use purple for this because it's blue and red. Let's do a little copy-paste here, just to show, number one, to cut down on the writing, but number two, to show you how similar this is, right? We're going to change that color to purple. Maybe, yeah, maybe we keep it at purple there, okay? So roughly 95% of the data is within 2 standard deviations. What did I write standard? I meant to say, sorry about this. This should have been standard deviation. This 2 should be standard deviation of the, you can't really read that. Standard deviations of the mean, right? So here, 95% of the data is within this interval. And last but not least, we know that almost all of the data, roughly, oh wait, no, you know what? Let me make this black so it pops a bit more. Is within, so this is almost all of the data. It's roughly 99.7. I think the book says almost all, but it's 99.7. 3 standard deviations of the mean. Okay. Now the nice thing is, the nice thing is that this works regardless of what the mean and standard deviation are, right? Even if we shift the graph around, it's still the same. Even if we increase or decrease the standard deviation, the proportions still hold. This is a really powerful observation here, and definitely something we should know. It's called the empirical rule. Now, just want to note, these approximations work only if the distribution is normal. Whoops, oh my gosh, normal-ish, right? So, one thing you can try to do, you can go and look at the data in example 1, right? That temperature data. See what the range is, right? See what the range is. See what roughly 68% of the data looks like. 95, 99.7. Try that. All right. Let's just actually super quickly, just get some graphs going. So let's just build a I don't know, histogram, right? Simple histogram of, let's try San Francisco's, right? And just see what that looks like, right? See, is that normal? Not really. What about St. Louis? That might look a little bit better. It's a little more distributed. Let's see. Not exactly. So maybe those aren't the best examples, given that they're not really normal. But that leads to our next problem, right? What if our data is not approximately normal, but suppose that somehow we do know our mean and standard deviation? Well, this leads us to Chebyshev's inequality. Chebyshev's inequality. Just Chebyshev's inequality. What Chebyshev's inequality says, for any distribution, normal or otherwise, the proportion of data within k standard deviations of the mean is at least 1 minus 1 over k squared. So in particular, 1 minus 1 over 2 squared, which is 3/4, at least 3/4 of the data must be within 2 standard deviations, or 75%, right? And 1 minus 1 over 3 squared, which is 8/9, which is approximately 89%, or let's say it's about 88 I'll just say about 89% of the data must be within 3 standard deviations. So suppose, whoops, we're not referring to this, we're referring to temperature data. Forgive me there. Suppose our temperature data is not normal, which it's not, frankly. What range of data must be within 2 standard deviations of the mean batting average? What about 3 standard deviations? Well, we know for San Francisco that the mean equals 57.5, and we know that the standard deviation equals approximately 3.9. Okay? So, using Chebyshev's inequality, roughly 57 I guess we could say roughly 75% of the temperatures are in the interval, and it's going to be 57.5 minus 2 times 3.9 to 57.5 plus 2 times 3.9. And what's that going to equal? That's going to give us, calculate, so that's almost minus 8. So 57 minus 5, that would be 49.5. You want to add 2 back on. So I think it's going to be 49.7. 2, and if you added 8, you would get 65.5. I think it's going to be 65.3. So at least, maybe I should say, I shouldn't even say roughly, maybe I should say at least 75% of the data is going to be within that range. Right? Now, it turns out, actually, that all the data is within that range, right? Because the standard deviation is very low. Okay? Oh, sorry. We knew that we knew that at least 75% was, right? So it turns out 2 standard deviations cover the whole thing. But we knew that it was at least 75%. And I'll just say try it for St. Louis. And that's all.